Hi, my name is Rémi Hutin, and I'm going to present our paper for CSF21 called Secure Compilation of Constant Resource Programs. This is a joint work with Gilles Barthe, Sandrine Blazy, and David Pichardie. The goal of our paper is to formally verify the preservation during compilation of a protection against side-channel attacks.
Timing side-channel attacks is a class of attacks for which an attacker uses the execution time of a program to deduce sensitive data. Cryptographic constant time is a well-known security policy used to protect against these attacks. Despite its name, constant time does not deal with execution time. Instead, to be constant time, a program must not perform any secret-dependent branch or memory access. This is a very popular policy which has been used to implement many cryptographic primitives. In order to formally define constant time, we first introduced a more generic policy called Observational Noninterference, defined in this paper from CSF 18. First, we consider an imperative language with a big step semantics. It reads as follows. Executing program P from state sigma leads to state sigma prime and produces leakage L. Different instantiation of L lead to different security policies. Next, we introduced a usual indistinguishability relation between states, verified if they share their public values. A program P is then considered to be only if any pair of executions starting from indistinguishable states produce the same leakage, here L1 and L2. Intuitively, a program is only secure if observing its leakage does not reveal any secret data. Constant time is then formally defined as an instance of ONI, where the leakage L is defined as a list of Boolean guards and memory accesses encountered during the execution. We illustrate it by giving the semantics rules for a true if statement. If a condition E evaluates to true, then the true leakage is added to the leakage produced by the executed branch. In our work, we consider a different instance of ONI, known as constant resource or time balancing. The leakage we consider is an abstract amount of resources consumed during an execution. In our language, every construct leaks a constant amount of resources. We also assume the resource consumption to be additive, as shown by the sequence rule. Executing a sequence of program leaks the sum of the individual leakages. The CR policy is less restrictive than constant time, and has been used to implement real-life cryptographic code. We illustrated it with an example inspired from Amazon's implementation of TLS. We consider a secret value x bounded between 0 and 32, and a function update consuming one resource. The following program performs x calls to update. The program then consumes x resources, which means that the secret value x is leaked during the execution. A way to repair it is to introduce padding. By adding 32 minus x calls to a function dummy update that does nothing but also consumes one resource, we ensure that resource consumption is constant and equal to 32. More generally, the CR policy allows secret-dependent branches as long as they are balanced. We can also say that CR is a relaxation of constant time, as any constant time program is also CR. A lot of work have been devoted to the constant time policy and program transformations. I list here a few works that are about either enforcing or repairing the policy by transformation or preserving it during a transformation. When it comes to the constant resource policy, there are several works about enforcing the policy. However, as far as we know, the problem of preserving the policy during a transformation has never been tackled. And this is the goal of our work. We met two main challenges that I sum up here. First, from the perspective of a compiler, the CR policy is very restrictive, as it relies on a fragile balance between resource consumption. Any common optimization performed in a branch could easily break the balance. This led us to introduce a more flexible security policy called TSharp that will be presented later. Second, from a proof methodology perspective, most of existing proof techniques used to prove that a transformation preserves a ONI policy cannot be applied in our case. Indeed, they all critically rely on a property on leakage called non-cancellation, which states that if two pairs of combined leakages are equal, then they are also equal element-wise. This is true for constant time leakage, but not in our case. A consequence is that a secure program may be a sequence of unsecure programs that balance each other. This makes reasoning about CR policy tricky, but I will not detail our proof effort in this short talk. During the rest of this talk, I will first present an example illustrating our approach. I will then motivate and define our new security policy, which is the main goal of this talk. Last, I will finish by giving an overview of our methodology to study the preservation of this policy during a compiler transformation. We present here an example that fully illustrates our approach. We consider the following program, which consists of a if statement and arithmetic operation over a few variables. We use a simple resource model that only takes into account addition and multiplication, and addition costs 1 resource and multiplication costs 2. The program performs 2 of each operation in both branches and is then considered balanced. However, it also performs redundant computations, as I times B is evaluated twice in the first branch, and same for A plus B in the second branch. An optimizing compiler would then be likely to perform a common subexpression elimination, leading to the following resulting program. The problem here is that the branches are no longer balanced. If the condition is a secret value, this transformation breaks the security policy. Our approach to adapt an existing transformation into one that preserves the CR policy takes 2 steps. First, we adapt the implementation of CSE into TSharp, which is identical but compensates any modification by introducing padding. Here, we introduce padding in both branches, denoted by a delta operator that consumes an arbitrary amount of resources. TSharp then preserves the resource consumption. Second, we apply a minimization pass that reduces as much as possible the delta operators in the program. Here, as delta operators appear in both branches, we can factorize them out. This pass is generic and independent of the transformation we are considering. Our approach restricts the compiler by introducing padding, but we want our compiler to be as efficient as possible. Ideally, we only need to restrict it in secret-dependent branches, and do not want to restrict it in other parts of the program. This would require the compiler to be aware of the taints of the variable. This is a challenging task, and a way to do it is to preserve a security type system during the compilation chain. It can be considered for a simple language, but as far as we know, no real-life compiler manages to preserve such type system for low-level languages. Our idea is the following. We introduce a syntactic annotation called atomic. This is inspired from synchronization points used in parallel computing. Our annotation statically identifies high security parts of the program. The compiler then considers this annotation to restrict its optimization. In practice, we represent the atomic annotation with a box notation around a statement of the program. Here, the second if statement is protected by the atomic. The compiler may adopt 2 behaviors. Inside atomic annotation, it is restricted and carefully keeps the balance between branches, as in my previous example. However, outside of atomics, it is not restricted. To capture these possible behaviors, we introduce a more flexible security policy called TSharp. It may also adopt 2 behaviors. Inside atomics, this policy behaves as the CR policy, which means that balanced secret-dependent branches are allowed. Elsewhere in the program, secret-dependent branches are never allowed, and the policy is then equivalent to constant time. We also formally define TSharp as an instance of ONI by combining elements from the constant time and the CR policies. Here, the leakage is a pair FQ, where F is a list of Boolean guards, similarly to the constant time policy, and Q is the amount of resources. The TSharp policy expects both the control flow and the resource consumption to be independent from secrets. This is relaxed by the semantic rule of atomic annotation. If a program leaks the pair FQ, then adding an atomic annotation removes the control flow part of the program from the leakage. In this case, the policy is relaxed down to CR. In other words, TSharp can be seen as a flexible mix between constant time and CR. To finish, I present our general methodology. To study a control flow preserving transformation T, such as CSE, constant propagation, or dead code elimination, we introduce TSharp, similar to T but which compensates any modification with padding. As T preserves both the control flow and the resource consumption, it preserves the leakage, from which we can conclude that it preserves the TSharp policy. Second, we apply the generic minimization pass, which removes as many delta operators as possible. Note here that any padding outside of atomics is simply removed. We proved this pass to preserve the TSharp policy, which was our main proof effort. To conclude, we presented a new security policy called TSharp, which is a flexible mix between constant time and the CR policy. The policy relies on syntactic annotations called atomic. Next, we developed a proof methodology to prove that a transformation preserves the TSharp policy. We then applied it to generic control flow preserving transformations. And last, all our results have been mechanically verified using the Coq proof assistant.